Hi, this is Rhonda Hughes at Bryn Mawr College, and we're going to do an example of a derivative where we require a little algebra that sometimes students may have forgotten. So let's take a look at the function f of x is equal to the square root of x, and we'll take the domain to be all x greater than 0. Now, of course, you can see that this function is defined when x is 0, but we want to look at the derivative, and that makes things a little bit different. So here's the graph of the function, y equals square root of x. And let's go ahead and use the definition of derivative to see what happens here. So we know that the derivative is the limit. I'll use this notation as h goes to 0, f of x plus h minus f of x over h, and let's remember what that is. If this is x, and this is x plus h, then that's f of x plus h, and that's f of x. And these quotients here are none other than slopes of secant lines that connect points nearby on the curve. However, when we let h go to 0, these lines get shorter and shorter and closer to this line that we call the tangent line to the curve. And the derivative, of course, is the slope of that tangent line. Now let's go ahead and plug in and see what happens. So in this case, we get the limit, as h goes to 0, of f of x plus h. Well, here's f of x, so f of x plus h is the square root of x plus h, all underneath the square root sign, minus the square root of x over h. Well, of course, our first instinct is to simply let h go to 0, but then what happens? Well, we get square root of x minus square root of x, which is 0, over 0, and that's a problem for us because we don't know how to define that. So we need some kind of little trick to go ahead and figure out this derivative. So before we do the trick, I want to remind you of something from algebra that's completely useful here and is going to get us out of this jam. Let's take a look at the algebra we need to make some progress on this problem. So I'm going to write down some rather mysterious looking things. Some A's, some B's, some A's, and some B's. That A should be red. Okay, and now what am I going to do? Well, I'm going to make this look like the difference of two squares, a squared minus b squared. And there's an extremely useful formula that tells us that we can factor this into the product of a minus b times a plus b. So if you check that by foiling or whatever method you like, you'll see that the AB's cancel and you're left with a squared minus b squared. So there we go. Now how are we going to make use of this particular formula? Well, let's take a look at this. Okay, we know that we're in trouble when we let h go to 0, but let's do what we call rationalize the numerator. So that's a lot to say, but let's rationalize the numerator. And what does that mean? Well, we can always multiply something by 1 without changing it, and you can write 1 any way you wish as long as the numerator and the denominator are the same. So let's multiply this by what we call the conjugate. It's the same thing but with a plus. Now, what's the point of this? Well, if you look up above, you'll see what the point is. So this is none other than 1, but this is our A, right? And this is our B. And now we have A minus B times A plus B. So in the numerator, what is that equal to? Well, let's come down here for a second. The square root of x plus h, which is A squared, is x plus h. And the square root of x squared is just x. So back here in our problem, when we multiply the numerators, these two things together, we have a minus b times a plus b, and we get a squared minus b squared. So we get x plus h minus x. So here's x plus h and here's x. Over this still more complicated thing, square root of x plus h plus the square root of x. So let's get rid of some of this so that we can finish our problem and see what we've got. You can take a look at that numerator and while I'm erasing, and I think you'll see that in the numerator the x's cancel, so all we have is h. And let me not forget over here, you were probably worrying about that, I still have that h in the denominator. So I now have h over h times the square root of x plus h plus the square root of x. And now, look what happens, that cancels, so there's just a 1 in the numerator. And when we take the limit as h goes to 0 here, something much better happens. This approaches as h goes to 0. What do we get? We get 1 over the square root of x, the h is gone, plus the square root of x, which is 1 over 2 root x. And that is the derivative of the function square root of x. And now you can see why we wanted x to be greater than 0, because this derivative does not exist at 0. So I hope that helped review a little bit of algebra, and we'll see you for the next problem.